Today we're going to talk about properties of equality and how to maintain equality in an equation. And we're going to write a few equations based on properties of equality. And we did a little bit of this when we looked at some of the problems with the coins and the money pouches, but I want to show you the mathematical rules behind some of the illustrations that we looked at. So first of all, I want to talk about identity laws. And identity laws have to do with what a number maintains as its identity. So think about it. If you had an identity, you would remain true to your identity, right? Every person has a unique identity, just like every number has a unique identity. And what we want to do with our identity laws is maintain our identity or keep it the same. For example, if I had the number 4, the identity of number 4, I want to remain 4. So the identity of the number 4 is equal to 4. I don't want to change the number 4 because that would not be the identity law, okay? In terms of adding and subtracting, what can I do with that number 4? What can I add to that number 4 to make it equal 4? Well, 4 plus 0 equals 4. If I turn the tables and I use that same example for subtraction, 4 minus 0 also equals 4. What that tells me is that the identity for addition and subtraction is equal to 0. So whenever I want to use the identity, whenever I want to get represent a number as itself, I can use 0. Okay? When I look at multiplication and division, it's a little different. Let's use 7. 7 times what number is going to give me 7? Well, 7 times 1 equals 7. Again, let's flip that example and see if it works. 7 divided by 1, well, that also equals 7. So the identity for multiplication and division is equal to the number 1. That's the number I would use in order to maintain identity in a multiplication or a division problem. So, what do I have to do to maintain equality or maintain my identity if I subtract something from the left-hand side of the equation? Okay, so I have an equation here. Here's my left-hand side, here's my right-hand side. I subtract 15. In order to equal out that equation, in order to maintain my identity, well, my identity for addition and subtraction is 0. So I need to make sure whatever I do on the right side of the equation gives me 0. So negative 15 plus 15, adding 15 to the right side of the equation, will get me 0. Right? So if you subtract 15 from the left-hand side, I'm going to add 15 to the right. Great. Let's keep going with those examples. If I added 10 to the right-hand side of the equation, what do I do to maintain equality? I subtract 10 from the left. So there are a few things that I'm looking at here. If I'm originally subtracting, I'm switching to adding. If I'm originally adding, I'm switching to subtracting. If I'm originally on the right-hand side, I'm switching to the left. And if I'm originally on the left-hand side, I'm switching to the right. So I need to pay attention to these rules when I'm thinking about equality in an equation. Right? What does the word equation means? One side is equal to the other side. So same kind of deal with division and multiplication. If I divide the left-hand side, in order to maintain equality, I need to multiply the right-hand side. So I need to multiply by 2 on the right. Last one, if I multiply the right-hand side by 5, I need to divide by 5 on the left. Okay, hope you're seeing that pattern there, that when we reverse the operation, we end up with the identity, right? And again, the identity for addition and subtraction is 0, for multiplication and division is 1. Now, this is a little out of focus, I understand. I apologize for that. This is the first set of coin problems that we worked on in class. So what it's telling us is that this coin here is a $1 gold coin, okay? and that this pouch could hold any number of gold coins, but we don't know what that is yet. We're going to have to solve for that in each of these problems. So each pouch in the equation contains the same number of $1 gold coins. That's important for us to know. The number of gold coins on both sides of the equality sign is the same, but some are hidden in their pouches. That's also important to know. And our goal here is to try to find the number of gold coins in each pouch. So let's look at this first example. I know that we did a few of these in class. If I have 3 pouches filled with unknown numbers of gold coins, I'm going to put X's through them so that I understand that I have X as a variable, and that equals the number of coins in each pouch. Great. I'm also going to think about my rules of equality. Okay, because I have some excess coins on this side that I don't want to have to deal with in terms of my math ability. They're in my way to solve this problem. So I want to remove these 3 coins from my equation. I want to know that if I had a scale, almost like a seesaw, and I decided, you know what, this seesaw is perfectly balanced right now, but I'm going to take away these 3 pink coins. Well, I'm also going to have to take away 3 pink coins from this side in order to maintain the balance, in order to keep the equality. So now I need to know how many coins are left over here. Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You can keep counting if you wish, but I know that I have 27 coins total left over after I removed those 3 pink coins, okay? So now this is a little simpler. I have 27 coins that needed to be divided evenly into 3 pouches. So how many coins can fit into each pouch? Well, I can write this out mathematically. 27 divided by 3 equals 9 coins in each pouch. So a problem that looked fairly complicated, thinking about rules of equality simplifies and helps us to solve for the correct answer. Okay? There's another example here that asks us to write an equation for this picture. Now, this is almost like what I did when I talked about X as being the number of coins in each pouch. Because what I need to know is if I have 5 pouches, how many X's do I have? Well, I have 5 X's. And when I write it like that, 5X, that really means 5 times X, or times the number of coins in each pouch, right? So 5X plus, I have 1, 2, 3, 4, 5, 6, 7, 8 coins, 8 $1 coins that have a value of 1, so I can use a whole number 8 there, equals however many coins are on the right-hand side. So right here I have 8, 16, 24, but without this one, so that would be 23. There's my equation. So now it says solve for the number of gold coins in each pouch. I'm going to use my rules of equality, right? 5x plus 8 equals 23. I want to use my identity law and take away 8 from this side so that I'm left with 0, so that it's a little easier for me to work with this equation. And by doing that, I need to pay attention to equality and remove 8 from the right-hand side as well. So 23 minus 8 equals 18. Now I have 5x equals 18. How many coins are going to be in each of those pouches? Well, x equals, oops, I'm sorry, that's not 18. That is 15. X equals 15 divided by 5. Therefore, x equals 3. So that's how I would write the equation and solve for this particular problem.